So now we're going to do our Brayton cycle question, and we'll do 6.3. An aircraft engine is operating on an ideal Brayton cycle with a pressure ratio of 15. Heat is added to the cycle at a rate of 500 kilowatts. The mass flow rate in the engine is 1 kilogram per second, and the air entering the compressor is at 70 kilopascals and 0 degrees Celsius. Determine the power output by this engine and its thermal efficiency, and assume constant specific heats at room temperature. Okay, so let's just have a brief look at what the Rankine cycle, we just did that one, what the Brayton cycle looks like. So going over to here. So the Brayton cycle is very similar in some ways to the Rankine cycle in that we have a compression, an isentropic. In this case, the compression process happens in the compressor of the jet engine. So that's the big spinny thing you see at the front, kind of. It's part of it anyway. So the air enters the engine. It goes through the compressor, and it goes from relatively low pressure through the compressor to a relatively high pressure. And this process is an isentropic process for a Brayton cycle. In the ideal case, this is an isentropic process. So that's just something to bear in mind. And then the rest of the cycle is exactly the same as the Rankine cycle in that we have an isobaric heat addition. So this is where we have our Q in. Then we go to state 3. And at this point, so now we've gone through our compression and our heat addition at a very high temperature, very high pressure. We've just come out of the combustion chamber. And we're going to expand now through the turbine. And the turbine we draw is just the opposite direction of the compressor. That was not very good. I think I can do a bit better. Let's draw it like this over here. And then we expand here to state 4. So this is, we go through the turbine where, again, just like with the Rankine cycle, at a lower temperature, at a lower pressure. And then we enter, in this case, so in Thermo 1, we're going to assume that the air doesn't get exhausted overboard, that it gets recycled. And this is where we have our Q out. So we're going to have this as a heat exchanger condenser where we have our Q out. Now, something to note, just like in the Rankine cycle, we do have a work output here. But the compression process for something with a low specific volume like air is, high specific volume like air is really, really demanding energy-wise. So a lot of this work out is going to get sent back to the compressor just to drive the compressor. So how it works is the compressor, just like we saw in the other question, is with a pump, though instead of a compressor. It's being powered by taking some of the work that the turbine does and using it for itself. And the rest of the work is the net work, and that's what you can do other things with. So whether it's an aircraft engine to generate, thrust or auxiliary power, or whether it's a ground-based gas turbine for power generation, that network that you get, you have to consider the amount of work that you bleed off to power the compressor. So we can start going through this question now. Let me reopen it on the other page there. There we go, 6.3. Okay, so this is going from state 1 to 2. We know at state 1, we're at 70 kilopascals and 0 degrees Celsius, so 273 Kelvin. Now, what do we know about state 2? Well, we don't know too much about state 2, but we do know that the process from state 1 to state 2 is an isentropic process. So if you remember from the Otto cycle video I did, we discussed what the difference between a polytropic process and an isentropic process is. So if you then, and we derived a couple of relationships for isentropic processes. So one of the relationships we derived, and I'm just going to write it over here again, is T2 over T1 is equal to the pressure ratio, which is P2 over P1 to the power of gamma minus 1 over gamma. And we said that gamma is the specific heat ratio. It's Cp over Cv. And for air, gamma equals 1.4. Now, whenever a process happens along this path, this is an isentropic process. So it's the same as a polytropic process with the added constraint that this exponent here, it depends on gamma, or 1.4 in the case of air, as opposed to just a different number. Anyways, we can use this to find the temperature and the pressure on the other side, because we're told, if you read the question, that we have a compression ratio of 15. So that means the compressor is going to take the pressure of the air at state 1 and multiply it by 15. So if we start at 70 kilopascals, we're going to go to 1050 kilopascals, right? And knowing now, of course, P2 and P1, and of course knowing T1, we can find T2 from this relation we just put over here. So T2 is equal to T1, if we cross multiply there, 273, and this has to be done in Kelvin, times P2 over P1. So I can either just put 1050 over 70, or I could remember that P2 over P1 is just the pressure ratio, which is given as 15. And then it's gamma minus 1 over gamma. That's our exponent. Now, if we calculate this, we end up with temperature 2 is 591.8 Kelvin. So we can just put that here, 591.8 Kelvin. Okay, so now let's start looking at state 3. Well, we're told that we're adding, in terms of heat, we're adding, I believe it was 500 kilowatts. Yes, it was 500 kilowatts of heat that we're adding. So if we remember Q equals mc delta T, or m dot c delta T, well, 500 kilowatts, so times 10 to the 3, equals m dot, and we're told m dot is 1 kilogram per second. Now, Cp for air, because we're talking about the change in enthalpy here, Cp for air is 1.005 kilojoules per kilogram Kelvin. So we'll do here 1005. Well, actually, let's just do this in kilo units because it's a bit easier. So 500 kilowatts equals 1 times 1.005 times the change in temperature. So we know the temperature at state 2. We don't know the temperature at state 3, but we're going to find it. This is how we're going to find it. And if you do this, what you should find is that the temperature at state 3 is 1089 Kelvin. So 1089 Kelvin. Now, what's the pressure at 3? Do we know the pressure at 3? Well, remember, the process from state 2 to 3 is isobaric, and we know the pressure at 2. So that means we also know the pressure at 3 is the same as the pressure as 2, or 1050 kilopascals. Okay, so we've defined state 1, state 2, state 3. This is good. But now we still have to define state 4. So in most cases, you can assume that when you expand through the turbine, you're going to expand all the way back to the ambient pressure. So that means that state 4 is going to be at a pressure of 70 kilopascals again. Now, we don't know the temperature, but remember, this process from 3 to 4 is isentropic, and whenever we have an isentropic process, the isentropic relations, including the one I gave here, applies. So if we just sort of recreate this same relation for the case of 3 to 4, we have T4 over T3 equals P4 over P3 to the power of gamma minus 1 over gamma. T3 is known, T4 is what we're trying to find. Now the pressure ratio 4 over 3 is going to be 1 over so it was a 15 pressure ratio on our way up, but on our way down, it's 1 over 15, because now we're not increasing in pressure, we're decreasing. So If we want to find T4, I'll just write it on the left. T4 equals 1 over 15 times T3, which we know, to the gamma minus 1 over gamma, where gamma is 1.4. And if we do this, we get a temperature of 502.3 Kelvin. Now, why did we go through finding the temperature and the pressure at every point? Well, in the case of the Rankine cycle, we were interested in the enthalpy at every point because it's the enthalpy that tells us about the heat transfer and the work done, but across each device. In the case of an ideal gas, what we're interested in is the temperature, because we remember that the work done or the heat transfer is m dot Cp delta T. So if we know the temperature at every point, we're in a pretty good position to start finding things like the heat transfer in the combustion chamber, in the condenser, the work transfer or the work done by the turbine. And this is all stuff we're going to eventually need to know to answer what they're asking. So the question itself is asking, determine the power output and its thermal efficiency. Okay, so I'm going to erase just a bit of stuff here so we have some space. Okay, so the power output is what happens in the turbine, but we have to consider that a good amount of that power is going to get rerouted to the compressor. So let's see what happens. M dot Cp delta T across the turbine corresponds to our 1 kilogram per second times 1.005 for air, which is Cp of air, delta T. So T3 minus T4. In other words, 1089 minus 502.3. Now let me calculate that. So 1.05, 1089 minus 502.3. So this comes out to a change in temperature of not a change in temperature, work done equals, I think I just made a typo there. Sorry, just made a calculator typo. So calculating this, we get 589.63 kilowatts. Now, before you get excited and say, okay, we're producing, network is 589.63. Remember, a lot of this is going to the turbine. So from this, to find the network, we have to subtract the work done by the compressor. And that's simply going to be MCP delta T across the compressor. So again, that'll be 1 times 1.005 in the case of air, times T2 minus T1. So 591.8 minus 273. And so this is work turbine, this is work compressor. 1.005 times 591.8 minus 273 gives 320.394. So if I want to find the net work, I have to take the turbine work, subtract the compressor work, and that's what I actually get to use. So 589.63 being the turbine work minus 320.394, which is the compressor work, leaves me with only 269.24 kilowatts that I can use. So just take a moment to see that the compressor takes up more than half the work done by the turbine. And this is something that's pretty common in these types of engines, because a very high specific volume gas or fluid of any kind really takes a lot more work to compress. So for this reason, a Rankine cycle, which works with a liquid, which is very low specific volume, it doesn't take that much work, and we can often even neglect the work that the pump does. But in the case of a Brayton cycle, you can never neglect it. In fact, it's often the case that the work output by the turbine is almost completely taken up by the compressor. So anyways, we found the net work. This is how much we actually get to use. It's left over from what the compressor doesn't want. It's 269.24 kilowatts. But if we want to find the thermal efficiency, we have to take the net work and divide it by the heat transfer to the system, the Q in, the amount of fuel that we need to burn to generate this. So 269.24 kilowatts is our net work output divided by the Q in. What's the Q in? Well, again, we're going to do MCP delta T. So we're going to do it across the not the boiler, the combustion chamber. So from 2 to 3. So Q in equals m dot, which is 1 kilogram per second, times Cp of air, which is 1.05, times temperature 3 minus temperature 2. So 1089 minus 591.8. 497.2. 497.2 times 1.05. And I'm getting 499.6. Oh, of course, my bad. They give us Q in the question. So I just calculated exactly what they gave us, which is about 500, which is 500 kilowatts. So actually this last step was unnecessary. But if they didn't give us Q in, this is how we would find it. Anyways, thermal efficiency is 269.24 divided by 500. And that gives us an efficiency of 53.8%. So 0.538